In this video, we will be solving the frame problem by the method FEM in MATLAB. So first we will discuss the approach to solve the problem. So in the first step, we will take the inputs, which are area of cross section, Young's modulus, like the inertia, number of elements NE, and nodes, number of nodes, that is ND, and the coordinates, like the coordinates of these nodes, like something like for the first node it will be 0 0, and then we will go to the other nodes uh, similarly, and then we will get the give this element connections, like 1 is connected to 2 and 2 connected to 3 in the simple cases. But as these are frame problems, there may be some problems where it may be a complex, so here we have to define the element connections. And we will also require, as this is a frame problem, it can also have this UDL, so we have to give this Q also. So after these in getting these inputs, we will start like making this stiffness matrix. Like we will initiate it as a square matrix of this size, like this is ND, so ND cross 3 into ND cross 3. So we will get this stiffness matrix. Like for the problem we will be discussing in this video, it will be 9 cross 9. Okay, so then we will like start with getting the node 1 information and then node 2. We will get this node 1 and node 2 through this we will go for this for loop, that will be like I is equals to 1 to any, that is number of element. So for the first element we will go to this this element connection, and we will get the first the first 1 1 of that matrix, and 1 2 of that matrix will give us the node 2. So these will be used for finding the coordinates, and from these coordinates we will get the sine cos values, and also the length of that member, as it can also be a inclined member. So after getting these things, we will form a like this uh, we will make this transformation matrix. And so we will first this element is stiffness matrix, and this will be multiplied, like it is equals to like T transpose into K into T for the global, like converting it into the global format. So we will then update this global element stiffness matrix into the global stiffness matrix. And after getting this, we will also in this we will also consider this RQ effect, which will be due to the this UDL. So we will also get this also, like okay. After this we will work for this K into D is equals to F. Then we will go for like D is equals to INV K into F. So we'll get these displacements, and after getting these displacements, we will get these moments and here, which we will be like we have these equations for them, and we will use them, and then we will plot them. Okay, so in this video we will be discussing this problem, where this is like first node, then second node, and this is third node. Each node have 3 degree of freedom, that is like u like x direction, y direction, and like theta. So these this global stiffness will be of 9 cross 9. So now we will move to the MATLAB part of the problem. Now we are onto the MATLAB part of the problem. So first, as I have already discussed, first we will define these constants, which are like area of cross section, Young's modulus, inertia, and a number of elements, that is 2 for this problem. As I have shown the problem to you, like the element 1 is an inclined member, and another element 2 is an horizontal member. So after this we will also get the number of nodes, which is in this problem is equals to NE plus 1, which is 3. Now we will get these coordinates of the members, like these nodes. So for the first node it will be 0 0. Then for the second node is I have already shown, it was like this. So this was like 6 meter from this x direction and 4.5 meter in y direction, and this third node is 12 meter in x direction and 4.5 meter in the y direction. So now we will move further, then after giving this coordinates, we will get this element connections, which is like 1 to 2 3, like they are directly connected. So 1 is connected to 2, 2 is connected to 3. So after this we will initiate this stiffness matrix, which is of the size nd cross 3, it is a square matrix. So after getting this, we will also, like, here I am defining force vector before, but usually it is defined after. But as I have also incorporated the RQ effect in the this first loop only, so I am defining this force vector here. So this q, as I have shown you the problem, it was UDL in the second element. So I have to also work for this q, q part also. So this q is 50 kilonewton per meter, and this rq element that this q is acting is on the second element. So I have defined it as second element. This is a very generic code, it can be used for any other problem also. So now we are moving on to the for loop. Like this will go from 1 to the number of elements. So node 1 is like m11, which is like member, like this m11 is like this element connectivity part, like this one. So this will equals to m11 is equals to 1, and m12 is equals to 2. So we get this for the first element, we get the node 1, that is 1, and node 2, that is 2. So after getting these nodes, we will directly get this dx and dy, like dx and dy like x2 minus x1, and dy is like y2 minus y1. So these we will, as we have already got this this element number, node number. So from this node number, we from this coordinates, so we will get this dx dy. So see node 2 1, like node 2 is here 2. So see node 2, like node 2 6 6. So 1, like 6 minus 0. So dx is 6 and dy is 4.5. Like this is just getting this uh, x2 minus x1 and y2 minus y1 in terms of this node 2 node 1. So after getting this, we will get this the length of the member, that is under root x2 minus x1 whole square plus x2 minus y2 minus y1 whole square, whole is an under root. So after getting this, we will get this sine and cos value, which are like I have used c and s for these sine and cos values. So like now we, like, after getting these sine and cos values, we will make this transformation matrix, which for the horizontal member will eventually turn into an identity matrix. So then getting this local stiffness matrix. So here we will require a area of cross section, Young's modulus, and this length of the member and inertia. So here here in the here I have defined this local stiffness function. So this is like just the function which can be directly used, which I am using here. Then there is nothing new here. So after getting this function, I am converting into the global coordinate, that is t transpose into k into t. So here it will be converted into the global stiffness. So now indexing is as I consider you have already watched the truss problem. So indexing here is similar to the truss one. There it was 2 node 1 minus 1, 2 node 1 minus 2 node 1, and 2 node 2 minus 1, and 2 node 2. So as there were only for one node there were two degrees of freedom. Here it is 3. So here we are using 3 node 1 minus 2, 3 node 1 minus 1, 3 node 1. So it is like for the first node it is like 3 node 1 minus 2, it will be like 1, 3 node minus 1, it will be 1, it will be 2, and 3 node 1 is 3. And similarly node 2 is 2, so 3 into 2 is 6, 6 minus 2 is 4, and 3 into 2 is 6 minus 1 is 5, then 6. So 1 2 3 4 5 6 for the first element. So it will be updated accordingly into the 1 2 3 4 5 6 and row, and 1 2 3 4 5 6 column. So then after updating, we also as I have told you, I have also incorporated this RQ effect in the in this first loop itself to minimize the computation. So I've just like this RQ local. So this is just an equation, like this is what we have defined. So we will convert it into the global form, and after converting it into the global, we will add this into the this force part. So index is same as for the this stiffness. So like here this is working for only I is equals to RK element. So when I is equals to 2, so and RK element is 2, so it will work. For I is equals to 1, it won't work. So means if there are two elements where there is UDL, it will automatically update itself. So this is a good thing, that this is a very generic code. It will work for other problems also. So now we will as all like the usual part, we will solve for the displacement. We will solve for the displacement, which will be in the global terms. So this is like we will the unknown displacement, that is 4 5 6, as the first and third node are fixed, so the unknown displacement are only 4 5 6. I have like transformed it to make it a vector, and then this inverse function is used to find the k inverse, and then multiplied with f force vector. So we will get this d like displacements. So after getting this displacement, I have also calculated for these movements. So moments like so as you know, we will go for s is equals to 0 to 1. So I have used this dt is equals to 0 0.01, ds is equals to 0 0.01, and I have like for the 100 points in an element, calculated it for the 100 elements, 100 points in an element. So the similar code, like it this part is similar to this stiffness part up to this as calculate sign and transformation calculation. Here after calculating this transformation, and index is also same. Just the difference is here we will convert this uh, global displacement into the local, to get the moment local, like the local element moment, and shears in the local terms. So we have used this loop for finding finding the moment, and then we have just used these equations. We have also considered this RQ effect, like this add fixed and moment due like this parabolic term, to for the second element, as this is we have we have used superposition for this, and after getting these moments, we have plotted them like this I have created this movement 2 cross the number of the points I have taken in PT, that is 100. So 2 cross 100. So this is movement. So first row is for the first element, and second row is for the second element. So after getting this, after get we have plotted them, and let me show how this works. And this is good to go, and this is the plot. Okay, so this is the for the element 2, and I think okay, so this for element 2. This is for the first element movement diagram. So here here it is continuous, as I have already included this superposition effect. So this is minus 50, and here in the first element it ends in minus 50, and it is continuous. So this is the end of the video. I hope you got this concept, and